Welcome to this presentation on reciprocating engines fundamentals. Today, we will explore the theory, operation, and design characteristics of reciprocating engines, key power plants that have driven aviation history and continue to power many general aviation aircraft. We'll examine engine cycles, energy transformation principles, fuel economy, reliability standards, and the critical considerations that influence engine selection and maintenance. Whether you're preparing for FAA certification or simply deepening your technical foundation, this session will provide a comprehensive overview grounded in the FAA's Airman certification standards. Reciprocating engines are at the core of most general aviation aircraft. These engines operate on the principle of converting chemical energy from fuel into mechanical energy through a series of linear movements. We'll be breaking down this concept by examining each system that supports engine functionality, from cylinders to propeller shafts. Understanding how these elements interact is essential for safe operation and effective troubleshooting. Stay tuned as we build from basic concepts to practical applications. To maintain level, unaccelerated flight, an aircraft must generate a thrust force that exactly counteracts aerodynamic drag. This balance is fundamental to flight mechanics. In a reciprocating engine, this thrust originates from controlled combustion, which pushes the piston down and turns the crankshaft. The crankshaft, in turn, drives the propeller, producing forward motion. Mastery of this theory lays the groundwork for diagnosing engine performance issues and optimizing efficiency. All heat engines, including reciprocating engines, share one fundamental principle. They convert heat energy into mechanical energy. This is accomplished through the movement of a working fluid, usually a gas-air mixture, that flows and expands through the engine. In a reciprocating engine, combustion occurs when the pressure and temperature are at their peak, typically just after the compression stroke. The resulting rapid expansion of gases forces the piston downward, converting chemical energy into useful mechanical work. Understanding this principle is essential for diagnosing performance issues and ensuring efficient engine operation. Engines are categorized based on several key principles. First, we consider the type of working fluid used in the engine cycle, whether it's air, a fuel-air mixture, or steam. Next, we examine how the engine transmits mechanical energy into propulsive force, such as through a crankshaft or jet nozzle. Finally, the method used to compress the working fluid, whether mechanically or dynamically, further defines the engine's classification. Understanding these distinctions helps technicians identify engine types and their operational characteristics. Engines are broadly classified based on how they operate and their configuration. In aviation, the most common types include reciprocating engines, gas turbines, and turboprops. Reciprocating engines use pistons to convert pressure into rotating motion, ideal for smaller aircraft. Turbine engines rely on high-speed rotating compressors and turbines, offering more power and efficiency for larger high-speed aircraft. When it comes to compressing the working fluid in an engine, there are two fundamental methods. The first is the turbine-driven compressor, commonly found in gas turbine engines, where rotating blades compress incoming air efficiently and continuously. The second method is the positive displacement compressor, seen in reciprocating engines, where a piston compresses air in a cylinder by physically reducing the chamber's volume. Each method has its own performance characteristics, suited to different types of aircraft. Understanding these systems helps technicians determine appropriate maintenance procedures for each engine type. Some engines rely on unique methods of compression to operate effectively. Ramjets use forward flight speed to compress incoming air. This is known as ram compression and is only effective at high velocities. As the aircraft moves forward, air is forced into the engine, compressed by speed alone without moving parts, and mixed with fuel for combustion. In contrast, pulse jet and rocket engines generate compression from the combustion itself. These systems build pressure internally through explosive ignition cycles, making them suitable for high-speed or spaceflight applications. In aviation, engine design must meet several critical general requirements to ensure safe and efficient operation. First, the engine must deliver high efficiency. converting fuel to useful work with minimal waste. Economy is also essential, providing the best performance per unit of fuel consumed. Reliability is non-negotiable, as engine failure in flight could be catastrophic. An ideal engine should offer a low weight-to-horsepower ratio, giving more power without adding unnecessary mass. It must sustain high power output continuously without compromising safety, and must also be durable enough to operate for extended periods between scheduled overhauls. In addition to performance and durability, an ideal aircraft engine must be compact, conserving space without compromising function. Ease of maintenance is another crucial factor. Components must be readily accessible for inspections, servicing, or repairs. A well-designed engine should also operate with minimal vibration, improving both comfort and mechanical longevity. Lastly, it should deliver a wide range of power outputs, adapting smoothly to varying flight speeds and altitudes to meet the demands of different flight conditions. This is referred to as flexibility. The general requirements of an aircraft engine directly influence the design of its subsystems, such as the ignition system. The ignition system must reliably deliver high-voltage sparks under all operating conditions. Next, accurate fuel metering devices are essential to provide the correct air-fuel ratio, ensuring optimal combustion efficiency and power output. Finally, the oil system must be capable of sustaining engine lubrication and cooling under the most demanding operating conditions. Each of these components must be precisely matched to the engine's performance expectations to ensure safety, reliability, and longevity. Power and weight are critical factors in aircraft performance. Thrust is the force that propels the aircraft forward, and it's measured differently depending on the engine type. Reciprocating engines are rated in brake horsepower, bhp, which reflects the usable output. In contrast, gas turbine engines are rated in pounds of thrust. To convert thrust to horsepower, use the formula shown here. Thrust times aircraft speed in miles per hour, divided by 375. This allows a meaningful comparison between the power outputs of different engine types. Fuel economy is a key consideration in aircraft engine performance, and it's typically measured using specific fuel consumption, the amount of fuel used per unit of power produced. At low speeds, reciprocating and turboprop engines are generally more fuel efficient than turbojet engines due to their design and lower operating RPMs. However, as aircraft speed increases, propeller efficiency drops, reducing the overall efficiency of reciprocating and turboprop engines. In these conditions, turbojet engines become more fuel efficient, making them ideal for high-speed, high-altitude operations. This graph shows the relationship between thrust-specific fuel consumption, TSFC, and flight Mach number for three types of engines: reciprocating, turboprop, and turbojet. At low Mach numbers, reciprocating and turboprop engines exhibit lower TSFC, making them more fuel efficient for slower speeds. However, as the Mach number increases, the fuel consumption of these engines rises sharply. The turbojet engine, on the other hand, maintains a relatively consistent TSFC across the speed range, and eventually becomes more fuel efficient at higher Mach numbers. This illustrates why turboprops and piston engines are best suited for lower speed ranges, while turbojets excel at high-speed, high-altitude flight. When we talk about an aircraft engine's reliability, we're referring to its ability to consistently perform at its rated output, regardless of the challenges posed by altitude or harsh weather conditions. Manufacturers achieve this level of dependability through meticulous design, rigorous testing, and continuous research. Reliability ensures that the engine will function as expected, while durability measures how long it can maintain that performance. In essence, durability is the lifespan of the engine under normal operating conditions, provided that reliability is not compromised. Together, these qualities are critical for safe, efficient, and cost-effective flight operations. TBO, or time between overhauls, is a key indicator of an engine's longevity. It varies depending on how the engine is used, specifically the operating temperatures, how often it runs at high power settings, and the quality of maintenance it receives. A well-maintained engine running within its design limits will generally reach or exceed its TBO. However, If an engine operates beyond its recommended TBO and an accident occurs, many insurance providers may refuse to cover the resulting damages. Therefore, respecting the TBO isn't just a matter of performance. It's also a matter of compliance, safety, and liability. In commercial aviation, engine reliability is strictly governed by the manufacturer's recommended TBO and replacement schedules. These limits are clearly defined in the operator's approved operations manual and must be adhered to without exception. Compliance ensures not just regulatory approval, but operational safety and efficiency. With proper maintenance and overhaul procedures, engine failures become exceedingly rare, underscoring the critical role of preventive care and strict adherence to technical guidelines. When selecting a power plant, aircraft design speed is a primary consideration. Reciprocating engines are typically ideal for aircraft that cruise at 250 miles per hour or below, making them well suited for general aviation and training aircraft. However, for aircraft that require higher performance or operate at high altitudes, turbo-supercharged engines are the preferred choice. These engines maintain power output by compressing intake air, allowing reliable performance even as air density decreases with altitude. Choosing the right power plant ensures optimal efficiency, capability, and safety based on mission requirements. For aircraft cruising between 180 and 350 miles per hour, the turbopropeller engine is the optimal choice. These engines provide significantly more power than piston engines, enabling higher performance at greater altitudes. With their ability to handle larger fuel loads and heavier payloads, they are ideal for regional transport, surveillance, and specialized missions. Turboprops also offer improved fuel efficiency and better climb rates, making them dependable for operations requiring both speed and endurance. Their versatility and economy make them a staple in both commercial and military aviation. Turbofan engines are the powerhouse of modern commercial aviation, capable of cruising from high subsonic speeds to Mach 2.0. They offer a blend of efficiency and performance, making them ideal for long-haul and high-speed operations. Turbofans are quieter than traditional turbojet engines due to their bypass airflow, which significantly reduces noise pollution. This quiet and efficient operation makes them a preferred choice for both passenger and cargo jets worldwide. Their advanced design ensures optimal thrust while minimizing fuel consumption at cruising altitudes. When it comes to maintaining aircraft engines, having the right documentation is critical. Maintenance publications are official documents that guide technicians in servicing, inspecting, troubleshooting, and repairing aircraft engines and systems. These include manufacturer-issued documents like maintenance manuals, service bulletins, and overhaul instructions, as well as FAA publications such as airworthiness directives and advisory circulars. Compliance with these documents ensures safety, airworthiness, and regulatory adherence. Every maintenance action performed on an aircraft must be backed by accurate and current documentation to ensure precision and accountability. At the heart of every internal combustion engine is the process of converting heat into mechanical energy. This transformation begins when gasoline is vaporized and mixed with air, then drawn or forced into the engine's cylinder. Once inside, the mixture is compressed by a moving piston and ignited by a spark plug. This controlled combustion produces heat energy, which pushes the piston and is ultimately transformed into mechanical energy to perform useful work. Simply put, the engine turns fuel into power through the sequence: heat energy to mechanical energy to work. Let's now look at the sequence that transforms chemical energy into mechanical motion inside a reciprocating engine. It begins with induction, where the intake valve opens and a fuel-air mixture enters the combustion chamber. Next is compression, where the piston moves upward, compressing the mixture for better efficiency. Then comes ignition, as the spark plug fires and initiates combustion. The mixture burns, rapidly expanding and driving the piston down in the power stroke. As the piston descends, it expands the fuel-air mixture and converts the pressure into mechanical force. Finally, in the scavenging phase, the exhaust valve opens to expel the burned gases, making the cylinder ready for the next cycle. This continuous loop powers the engine efficiently and reliably. When the compressed air-fuel mixture is ignited inside the combustion chamber, it produces a rapid expansion of hot gases. These expanding gases apply a powerful downward force on the piston, initiating the power stroke. As the piston moves down, this linear motion is transferred to the crankshaft. Through a system of connecting rods and crank throws, that straight-line movement is converted into rotary motion. This rotary output is what ultimately drives the propeller or other aircraft components. The bore of a cylinder refers to its internal diameter. This dimension is crucial for determining the engine's displacement and, ultimately, its power potential. On the other hand, the stroke is the distance the piston travels within the cylinder. It moves from the top dead center, or TDC, which is the highest point of travel, to the bottom dead center, or BDC, the lowest point. Together, the bore and stroke define the engine's physical geometry and directly affect its torque and RPM characteristics. A longer stroke typically offers more torque, while a wider bore allows for larger valves and improved airflow. Aircraft reciprocating engines operate on one of two fundamental cycles: the two-stroke cycle and the four-stroke cycle. In a two-stroke cycle engine, the entire operating cycle is completed in just one revolution of the crankshaft. This means only one upstroke and one downstroke of the piston are needed to perform all the essential events: intake, compression, combustion, and exhaust. Because of this, two-stroke engines deliver a power stroke with every revolution, offering a higher power-to-weight ratio compared to four-stroke engines. However, this efficiency comes at the cost of fuel economy and emissions control. These engines are commonly found in lightweight aircraft, drones, and some auxiliary power units. While the two-stroke cycle offers simplicity and higher power output per revolution, most certified aircraft do not utilize this engine type. Instead, they are typically found in home-built or experimental aircraft due to their lighter weight and simpler design. Despite the operational differences, the core components, such as pistons, cylinders, and crankshafts, remain similar to four-stroke engines. The main distinctions lie in how fuel is delivered and how the valves are arranged, often eliminating complex valve systems altogether. This design reduces weight and cost, but also impacts durability and emissions control. What you're looking at is a typical two-stroke cycle aircraft engine, such as those used in ultralight and home-built aircraft. This compact Rotax engine showcases the simplicity and lightweight construction that make two-strokes desirable for specific aviation applications. Unlike four-stroke engines, this engine completes its power cycle in just one revolution, providing a higher power-to-weight ratio. However, it requires a precise fuel oil mixture and regular maintenance to ensure reliability. The visible carburetors and air intake system illustrate the basic fuel delivery mechanism used in many two-stroke designs. This diagram illustrates the two main strokes in a two-stroke engine. In the intake/compression stroke at the top, the piston moves upward, compressing the air-fuel mixture in the combustion chamber while drawing a fresh charge into the crankcase through a reed valve. Then, in the power/exhaust stroke shown below, the compressed mixture is ignited by the spark plug, forcing the piston downward. This downward motion performs two jobs, producing power and simultaneously pressurizing the new mixture in the crankcase. As the piston nears bottom dead center, it uncovers exhaust and transfer ports, allowing burnt gases to escape while the fresh mixture is forced into the cylinder for the next cycle. This simplicity is what makes the two-stroke engine lightweight and powerful for its size. Let's take a closer look at the four-stroke Otto cycle, which is the operating principle behind most aircraft reciprocating engines. The first stroke is the intake stroke, where the piston moves downward and draws in a fuel-air mixture through the open intake valve. The second stroke is the compression stroke, during which the piston moves back up, compressing the mixture to increase its energy potential. Near the top of this stroke, the mixture is ignited by a spark plug. That brings us to the third stroke, the power stroke, where the rapid expansion of combustion gases forces the piston down, producing mechanical work. Finally, the fourth stroke is the exhaust stroke, where the piston moves up again and expels the spent gases through the open exhaust valve. These 4 strokes complete one full operating cycle over 2 revolutions of the crankshaft. This diagram provides a detailed look at the 4-stroke cycle as it occurs over 2 full revolutions of the crankshaft, a total of 720 degrees. The cycle begins with the intake stroke, as the intake valve opens before top dead center and remains open past bottom dead center, allowing for optimal fuel-air mixture entry. Next is the compression stroke, where both valves remain closed and the piston compresses the mixture. Just before top dead center, ignition occurs, typically 20 to 35 degrees before TDC, initiating the power stroke. Combustion drives the piston down, generating mechanical energy. The exhaust stroke follows, with the exhaust valve opening before bottom dead center and closing after top dead center, efficiently expelling combustion gases. Note the valve overlap at the end of the exhaust stroke and the beginning of the intake stroke, a key feature for enhancing engine breathing and efficiency. This video shows a more interactive understanding of how 2-stroke engines operate. These animated resources bring engine theory to life by visually demonstrating each phase of the engine cycle in motion. This video shows a more interactive understanding of how 4-stroke engines operate. Diesel engines for aircraft aren't new. In fact, they were used in the past, but eventually discontinued. However, with leaded aviation fuel nearing extinction, some companies are revisiting diesel power development as a cleaner and more sustainable alternative. These engines typically use a fuel type similar to turbine fuel, making them a practical option for the future. One of their key advantages is high compression ratios, ranging from 16 to 1 to 20 to 1. Significantly higher than the 7.5, 1 to 9 to 1 ratios found in typical avgas engines. This high compression contributes to better fuel efficiency and greater thermal performance. This brings us to the end of this instructional session. The reciprocating engines remain a vital part of aviation propulsion, offering versatility, reliability, and efficiency across a wide range of flight conditions. From understanding combustion cycles to assessing engine performance parameters like specific fuel consumption and time between overhauls, today's discussion highlights the technical knowledge required of every aircraft maintenance professional. I encourage you to continually consult FAA-approved publications, manufacturer manuals, and regulatory updates as you build your expertise. Thank you for your attention, and keep striving for excellence in aircraft engine maintenance and safety.